Okay, apologies for the poor lighting, but here's a quick video covering a couple of things we did in the last week of term. I know a number of people were poorly or off doing other exciting things. So yeah, here we go. Firstly then, do me a favour, sketch for me the graph of sine from 0 to 360 degrees, cos from 0 to 360 degrees, and then tan. Well, tan's always a bit different, isn't it? So I always just remember tan looks like that from minus 90 to plus 90. So sketch tan from 0 to 360 using your calculator. Okay, so pause the video at this point and come back when you've done that. Okay, so hopefully those are all right. Sorry, my camera isn't coping very well with my calculator screen, but there we go. That's your tan curve. So that's the tan curve that I always remember from minus 90 to plus 90. Calculator's giving it to me from 0 up to 360. It's a repeating pattern. It repeats every 180 degrees. Right, what I want you to do is imagine that an angle is starting at 0 and slowly getting bigger, moving anti-clockwise, going up to 90, 180, 270, and then 360. In each of these quadrants, I want you to consider the value of sine, cos, and tan. So between 0 and 90 degrees, sine is positive. Between 0 and 90, the sine of an angle, this is 90 degrees here, is positive. So is cos between 0 and 90. So is tan. So they are all positive between 0 and 90. Between 90 and 180, well, sine is also positive. That's part of the curve from 90 to 180. If sine is positive, cos, however, is negative. It's gone negative, and so is tan. So only sine is positive. So again, see if you can pause the video and complete these two quadrants. We want to know which of the three are positive in that range of angles. Pause and have a go. Okay, so between 180 and 270, sine is negative between 180 and 270, as is cos, but tan is positive, so it's just tan that's positive there. And then between 270 and 360, sine is still negative, cos is positive, tan is negative, so it's just cos. And this is called the cast rule, C-A-S-T. And it's important to be able to identify between these key angles whether sine, cos and tan are positive. You'll see why in a short time. Okay, that was the first thing we did. The second thing we did was to do with identities. So, this expression here, sorry, it's blue. This expression here is an equation. It is only true when x is 3. This is also an equation. There are only certain angles that have a sine of 0.5. I mean, actually, there are an infinite number of angles, because if we go back to our sine curve, 0.5 is about there. So there are two angles that have a sine of 0.5 between 0 and 360, but the graph carries on, doesn't it, forever? But this is only true for certain angles. Equations are statements that have an equal sign, but are only true for certain values of x. Okay. That statement is true, whatever the value of x. That's always true. Similarly, that's true, whatever the value of x. Statements like that are referred to as identities. And sometimes identities are identified with a triple equal sign. I had to sound very bad at remembering to do a triple equal sign, but That's one way you indicate it's an identity. There are a number of identities relating to sine, cos and tan, and it's those that we are going to talk about. So what I'd like you to do is, on your calculator, I'd like you to sketch for me the sine of x squared. And on the same graph, I'd like you to sketch the cos of x squared. And I suggest you go from 0 to 360. So again, pause the video, have a go at doing that for me. Okay, so there you go. If I draw them, that's what we've got. So the sine of x squared is the blue one, and the cos of x squared is that one. Now, I can't help noticing that as sine of x squared gets bigger, cos of x squared gets smaller. And then when cos of x squared becomes 0 and sine of x squared is 1, the reverse happens. Cos of x squared gets bigger, sine of x squared gets smaller. I wonder what happens if I add the values of those two curves together. So I'm going to plot a third curve that is the sine of x squared added to the cos of x squared. This line here is that third curve. It is always equal to 1. Whatever the size of the angle, the sine of x squared plus the cos of x squared is 1. And this gives us our first identity. The sine of x squared plus the cos of x squared always equals 1, whatever the size of the angle. And actually, we have a different way of writing this. This is a sort of a convention, a tradition. It's a little bit quicker than this. We actually write that like this. And we say sine squared x. That's how we say it. So this is just the correct way of writing this. It's still this, though. It is the sine of an angle squared. And then similarly, we have this, which we say as cos squared x. So this is our first trig identity. Sine squared x plus cos squared x equals 1. And what this gives us is a relationship between sine and cos, which we're going to use in a moment. There's a second identity, which we did derive in class. I'm not going to derive it now, because otherwise this video is going to be interminably long. But if you take the sine of an angle and divide it by the cos of an angle, regardless of what that angle is, you always get the tan of an angle. Again, you could check that on your calculator by sketching sine x divided by cos x. You'll find you get tan x. So that's another relationship between sine and cos, which brings in tan as well. So we've got these two identities which we need to be able to recall. And in addition to that, we've got the cast rule. And so what we're now going to do is a question that uses both of those things together. Okay? So here's the question. Given that sine theta is 2/3 and theta is obtuse, find the exact value of cos theta and tan theta. Now, what we're not allowed to do, and we're not allowed to do it because it's only recently the calculators have been able to do this accurately, is just do shift sine to find theta and then do cos of that angle and tan of that angle. We're going to use our identities to work that out. Firstly, theta is obtuse. Obtuse is an angle between 90 and 180, so we're in this region here. So I know that the sine of the angle is going to be positive. Well, yeah, they've told us that in the question. Sine of theta is 2/3. But what that also tells me is that they're asking me to find cos theta and tan theta. They're both going to be negative because between 90 and 180, cos and tan are both negative. Only sine is positive. Okay, so here's what we do. So sine theta, and hopefully you remember the use of theta to represent missing angles. Sine theta, we're told in the question, is 2/3. So I'm going to use this identity here. And I'm going to rearrange this identity to get cos squared theta is 1 minus sine squared theta. Can you see how I've got to that? If we take this identity here and take away sine squared theta from both sides, you get cos squared theta is 1 minus sine squared theta. I want to find cos theta. If you remember, that's the first part of the question. What's cos theta? So cos squared theta is 1 minus, well, remember how we work out sine squared? All it is the sine of x squared. In this case, it's that squared. 2/3 squared is just as simple as squaring the numerator, squaring the denominator. And I can do that in my head because 1 is 9/9. I'm going to refocus. Hang on a minute. Sorry, I seem to have lost my focus a bit. There we go. Now, if cos squared theta is 5/9, cos theta will be plus or minus the square root of this. Except I know that between 90 and 180, cos will be minus. So that means I haven't got to worry about two answers. There's only one answer. And the square root of that, well, it is as simple as square rooting the top and the bottom. I don't know what the square root of 5 is, but I do know the square root of 9. So I now know what cos theta is. So I've got sine theta. I've used my first new identity to work out cos theta. I'm also asked in the question to work out tan theta. So that's where I use this. So tan theta is just equal to sine theta over cos theta. You don't have to justify this or prove this, just like I didn't prove or justify this. These identities are well known and we can just use them. So 2/3 divided by minus root 5 over 3. Of course, you can type that in on your calculator, but don't forget dividing fractions is the same as multiplying by. So we get minus 2 over root 5. But of course, if your calculator would have done that for you. So I have given sine theta and been told that it's an obtuse angle, worked out cos theta, and I've worked out tan theta, both of which are negative. Okay, so here's one for you to try yourself. Press pause and have a go. Okay, so reflex angles are between 180 and 360. So I know that sine in that whole area is negative. All right, so I'm going to work out sine first. So I'm going to use that first identity, but this time I'm going to rearrange it differently. So here's the identity. So I'm going to rearrange it this time to say sine squared theta is 1 minus cos squared theta. So remember, that's the opposite to what we did here, where we rearranged it like that. This time I've rearranged it like that. You need to become really familiar with those two rearrangements of this basic identity. Okay? 1 minus, well, if that's cos theta, cos squared theta is just that squared, so that's 9 over 16. So that means that sine squared theta is, well, that's 16 over 16. Take away 9 over 16, so that's 7 over 16. But remember I said reflex angle, sine will always be negative, so that means that the sine of theta is minus square root of that. I don't know the square root of 7, but I do know the square root of 16. And of course, I don't know, well, actually, I do sort of know that the fact that cos theta is positive means it's going to actually be between 270 and 360. But I don't need to worry about that because all I now know is I know cos theta, I know sine theta, so tan theta is equal to sine theta divided by cos theta. And this time I'll just use my calculator. So I'm going to hit the fraction button, hit it again, minus root 7 over 4, hit the fraction button again, 3 over 4, minus root 7 over 3. Bingo. So I've introduced you to the cast rule, I've introduced you to this identity, which has two rearrangements, this one, and I've introduced you to the second identity here, and we've used it to solve problems of this type. That is all you missed. Have a good Christmas. Take care.